Yo, what is up, guys? Welcome back. I think episode 109 today. We're gonna keep grinding. It's Friday today, so pretty happy about that. Let's take a look at our Pokemon of the day. Right, 109 today. So we got a coughing. Let's take a look at the sound. Ooh. Might be installing Linux this weekend if I get some time. So we'll see. Coffee. So you can see all my Linux stuff. Coughing. 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 Alright, there you go. There's our sound. Let's take a look at a quote today. We got this guy. Quote of the day. Okay. Looks like we got a chess piece here. No, we don't. Here we go. Quote of the day. I never dreamed about success. I worked for it. There you go. We just got to keep grinding, dude. Nothing's given to you. You got to work for it. Read that one more time. I never dreamed about success. I worked for it. So there we go. Cool stuff. Oh, I was just trying to search up who this person is. Oh. Esteed Londa person. American businesswoman. Wow, 96. Oh, 95, but about to be 96. It's impressive. Cool, man. Okay. Let's take a look at our roadmap today. Actually, I think we'll take a look at our first problem here. We got push dominoes. It is a medium problem, so I feel like we got to take a look at it. There are n dominoes in a line. We place each domino vertically upright. In the beginning, we simultaneously push some of the dominoes either to the left or to the right. After each second, each domino that is falling to the left pushes the adjacent domino on the left. Okay. Similarly, the dominoes falling to the right push their adjacent dominoes standing on the right. Okay. When a vertical domino has dominoes falling on it from both sides, it stays due to the balance of the forces. For the purpose of this question, we would consider that a falling domino expends no additional force to a falling or already fallen domino. Given a string of dominoes representing the initial state where dominoes I is equal to left, if the ith domino has been pushed to the left, dominoes I are if the ith domino has been pushed to the right, and dominoes I dot if the ith domino has not been pushed. Return a string representing the final state. Okay. This is definitely a bit of a confusing question, I think. So we go right, right. Dot is the ith domino has not been pushed. Right, right. Dot left. Push some of the dominoes either to the left or to the right. Okay, we have a dot and L. So we have LL. Okay. Then we have a dot. Then we have R. We push. Well, no, it's not to the right. Right, so we see a dot. We push this to the left, so it'd be LL dot R. LL, and we have a dot. Okay. Stands for the standing one. This one doesn't move because we have a left and a right. One's going left, the other one's going right, so there's nothing pushing on it. Then we have a dot standing domino. We push right. Okay. We have another dot. I feel like we'd push right again. No? I don't know. Maybe we have to go from this side. Start over here. So we have dot 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 L. Right? And we have a dot. We push that. Then we have a dot. LL. This dot turns right. Right. LL. I'm not getting the test case, bro. Like, my first intuition here without even doing this problem is that I think this is probably a stack problem. I think we can somehow keep track of our... I think. I'm not really sure, to be honest, but that's just my initial guess so far. Without, I don't really fully understand the question yet, so I feel like once I do that... Okay, we have 7 here. Push at index 6, it goes L. Okay, at index 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Index 8 is R, pushes right at index 9. Okay. Index 11 is L. Pulls at index 10. At index 6 and 7. Okay, let's open this in Paint. I feel like this is better. So this is our original, right? Oh. What's the input? Okay, the input is, whoops, dot L dot right dot that's bad, dot L R dot, 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 L, dot, dot. Okay, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So in our first test case here, we have L, L. So we're going to have a double L here, right? So we have L, L, right? Index 3 is R. So we're going to make index 4 R. Okay, so we have a dot, R, 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 dot. Index 3 is R. It will push domino at index 4, right? Index 7 is L. I think this is a dot. Index 7 is L, pulls left at index 6. So then we have L, L. We have 8 and 9. We have R, R. Let's redo that one. R. And then we have index 10. So 11 is 10, pulls at index 11 is L, pulls at 10. Alright, so then we go, okay, well, L, L. Then we have dot, dot. Okay, so that's what it looks like now. That's 6 and 7. We have an interaction here. Let's highlight them. We have an interaction. And another interaction here. Right, another interaction here. And then obviously you can't go this way and do these ones, right? Okay, now how do I think about, now I understand the problem. So now how do I think about this, right? So I guess we loop through this, right? Let's switch color here. We start here, okay? All right. If we see a dot, and then the next value is this, then we can make this one an L. All right, then we see a dot. If we see an L, we make this one an L. If not, we see a dot, we leave it. We check the next value, right? If we see an R, then if the next one's a dot, then we can make that one an R. Right, I guess that's really what we're looking at, right? If we see a dot first, we check if it's an L. If we see an R first, then we check if it's a dot, right? right? That would work, but what if there's a I mean, there could be something else, right? There could be two dots, right? So there could be, we could have a dot here and there could be an L here, right? I don't know what data structure to do here. I'm thinking here we could loop through and use a stack, right? Loop through, use a stack, and we can check, okay, stack -1 is a dot and this number is an L, then we stack -1 can be an L, right? We can change it like that, right? But if we see a dot, yeah, I think it's a stack. Let's check. 2-pointer string dynamic programming. Okay. Go through the dominoes from left to right. If you see an R, you start applying a positive force. If you see, Okay. Okay, so if dom in O's I forces I in range length dominoes, if dominoes I is equal to R, if the I you start applying as a positive force for each step after that. Alright guys, I'll be 1 second. Someone's gonna call me on the phone, so I'll be back in a second. So guys, I'm back. I don't know what is wrong with me today. I'll take a look at Leetcode because I'm not sure.
We have a dangerous threat.
He has sharp teeth. He has claws.
He escaped.
He's not from our world.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem push dominoes. There are n dominoes in a line and they're placed vertically, but some of them could be either leaning to the left or leaning to the right. And after each second passes, each domino that is, leaning, I say the word leaning, but they say falling to the left, pushes the adjacent domino that's to the left of it. And the same thing with dominoes that are leaning towards the right. If there were two adjacent dominoes like this and this, right, like how this one is leaning to the right, this one is leaning to the left, if they were leaning like this, then they would get stuck, right? One isn't going to fall over because they're both kind of pushing against each other. If there was a domino in the middle between these, they would be leaning against the one in the middle, and then the one in the middle would stay standing up. So basically, there are three states that a domino can be in. It can either be standing straight up, which is the simple case, right? And that is represented by a dot. And then left is meaning that the domino was pushed to the left. So this domino is pushed to the left. Now, a domino that's pushed to the left could, be falling. It could be stuck like this one over here, right? This one is stuck leaning in the left position. Or it could be like this one, which is leaning to the left, and then maybe it actually just completely falls over to the left side. That is also considered a status of L. Like that state is included in this. So if it fell over to the left or it's just leaning to the left, it's still represented by a L. And that's actually a very important point that we're going to use in this problem, because it basically tells us that if a domino was initially leaning to the left, its state is always going to be left, because it's either going to get stuck in this position or it's going to completely fall over. In both cases, it's still left. Similarly with dominoes that are leaning to the right, if it's leaning to the right or if it falls over, it's still considered R. Okay, but enough abstractions, let's get into an example. Actually, before we do that, remember what we're trying to do is get the final state of the dominoes. I didn't mention that yet, but that's pretty much what we're trying to do. Each second that passes, a domino could potentially, get stuck like these ones, or if there was, this domino leaning to the right and this domino, maybe this domino will push this one over. But let's take a look at an example. Okay, so now let's take a look at a couple examples. The first one is pretty simple, so let's just start with it. So we have R dot L, so that means this domino is leaning to the right, this is leaning to the right, this is straight up, this one is leaning to the left. So after each second passes, each domino is going to tip over. Well, after 1 second, what's going to happen? Well, not much is going to happen. With these three dominoes, you can see they're both going to push up against this one at the same time. So pretty much they're going to get stuck like this, right? These 3 dominoes are going to get stuck. This one's not going to move. It's going to stay standing straight up. But this one is just going to fall over, I guess. I don't know if it's going to push against this one, because this one should push up against this one, but they're both already falling to the right, so it doesn't really change anything. I mean, maybe this one will completely fall over, but the state is not going to change, and that's the important part. The state here is still R dot L, so nothing really changed. But the second example is a bit more interesting. So the question is how to even approach this problem in a systematic way. Well, one thing I mentioned first was pretty important. Anything that starts out as left or right is always going to stay in that state. So we're trying to look for the return state that we're going to, return the dominoes in. Well, we know that these ones that I've highlighted are not going to change at all. What we have to figure out is, what about the remaining ones? How are they going to change? And how can we do that? Well, there's actually multiple solutions to this problem, and you can check out some of them officially on Leetcode if you want. One that they didn't mention though, I think is the simplest, and it's actually pretty much the brute force. Not really brute force, but it's actually more of a simulation, right? Because this is the state that we're given, right? These are the dominoes that are leaning. And so of course, the ones that are standing straight up, they're not going to knock each other over. Only these dominoes that are left or right could knock other dominoes over. So these are the ones we should pay attention to. And by simulation, what I mean is, we should check on the first go around, basically simulating a second, right? 1 second, what's going to happen after 1 second to our dominoes? To figure that out, we should probably look at these dominoes that are leaning over right now. And maybe these dominoes are going to knock other ones over. Maybe this domino is going to change to being right. Then on the second, we should look at what that domino is going to do now. So basically, with each second, we're going to have a queue of dominoes that we're going to look at. Right now, our queue is these ones that I've highlighted. These are the ones we have to look at and see how they're going to affect the dominoes that they are adjacent to. So I'm not going to draw out the entire thing in the interest of time, but we will code up the official solution. But what we're going to say now is that these ones left, right, and all these have been added to a queue, right? And we're going to process them in our queue. We're just going to do this from left to right because it's simple. We could do right to left if we wanted as well. But it is going to be important for us to do them in order. We should either do left to right or right to left, and you'll see why in a second. But now let's start at the left one. Okay, this one is leaning to the left. It's going to fall over to the left. The first thing we should ask ourselves, is there anything to the left of it? Yes, there is. Is that domino standing straight up? Yes, it is. So what's going to happen now? Well, this domino is going to knock over this domino. Yeah, so what we should do now, let's say this has been popped from our queue so we don't have to look at it again, and it'll obviously never knock over any different dominoes, but this one over here now is going to be a left domino. But the question you might be wondering is, if a domino is falling over to the left, right, this one left, what if there was another domino to the right that was falling over there? So in that case, this one in the middle would not be changed to a left domino. It would actually stay the exact same. Well, that's why the order comes into play. We know that since this is the first domino, that there weren't any dominoes to the left of it that could have knocked it over to the right. And we know that because we started all the way at the left. But if we do get any dominoes that are leaning to the right, we don't know for sure that there isn't a left domino to the right of it that could make the one in the middle stand straight up. And that's the example that we're actually faced with next. Now we have a right domino. And so it's leaning to the right. What is to the right of it? A domino standing straight up. So of course this one should be changed to right. But before we confirm that it should be changed to right, we should look at the domino actually one space over and confirm that this is not a left domino. In this case, it's not a left domino. So we were correct. This domino in the middle is going to be to the right. But if there was a left domino over here, then we would not have changed this one in the middle. But for now, let's cross this out, and then let's go to the next domino in our queue, which is going to be this one that is leaning to the left. And we look at the value to the left of it. It's a domino standing straight up, so it's going to be changed to a left domino. Again, we didn't have to check the value to the left of it to check that it was a right domino, because we only have to do that with right dominoes anyway. And that'll probably make a bit more sense when we actually get into the code, because it's kind of hard to kind of explain in words exactly what I mean. But basically what I'm saying is, if there was a right domino over here, then we would have detected, okay, there's a left domino over here. and then we would have said, okay, then the one in the middle is standing straight up. So then on the next iteration, when we'd pop from our queue, we'd actually just skip this domino because we already know that these two dominoes counteracted each other, and then we'd go to the next domino. But that wasn't the case, so we don't have to do that. But that's why anytime we have a left domino, we don't actually have to check what came before it.
There have been students from various schools playing in the golf course construction zones, and some of them are wearing Abbott uniforms,
And you would like us to get our...
Okay, now to this domino. Oh, by the way, we're done with this one, so let's cross it out. Now to this right domino, let's kind of fast forward. Okay, there's a standing straight up domino. What about what comes after it? Is there a left domino here? Nope. So in that case, this domino is actually going to be changed to a right domino because this one tipped this one over, and then we're done with this one, and then we get to our last domino over here, and this domino knocks over the one that's to the left of it, so that one becomes a left domino, and then we're done with that. Now notice how all of that happened within 1 second. That was our first iteration through our queue, and in 1 second we updated the state of all the dominoes. But remember, we're not looking for 1 second. We're looking for the final state of the dominoes. How do we even know if we reached the final state? Well, basically after our queue is empty, because right now we have a bunch of new dominoes that were just tipped over. Either these dominoes are going to be standing, going to basically be caught together, basically stuck, or they have been knocked over to being flat. But basically, to figure that out, we will have to continue through this queue. Okay, first domino over here, it's leaning to the left. There's nothing to the left of it though, so I guess this domino didn't really do anything. Obviously its state didn't change, it's still a left domino, but we don't have to look at it in our queue anymore. Okay, next domino is a right domino. Okay, so we look at what's to the right of it. It's a domino standing straight up. But now, is there another domino that's leaning to the left? The reason we're checking that is because in this case, that would mean that two dominoes are causing the one in the middle to be stuck, and that's exactly the case here. So in this case, this right domino over here is not going to knock this one over because there's a left domino over here, so it's going to be standing straight up. So in this case, we do pop this from our queue, but this one does not change. And since we already saw that this domino is leaning to the left and it's causing this one to be stuck, we don't even have to look at this one. We actually skip this domino. So we pop this one even though we didn't do anything with it because we know that these two caused each other to be stuck. You'll have to pay attention to how I handle this in the code. It's actually pretty simple in the code, but it's kind of hard to understand the intuition of why we're doing this. Okay, next we have a right domino. So we look at the one that comes after it. It's not a domino that's standing straight up, it's a left domino. So we don't do anything. So what we would say with this right domino is, okay, we can't knock it over, so we don't do anything. So we just pop this from our queue. Then we check this left domino. Is this standing straight up? Nope. The one that came before is not standing straight up, so we can't do anything either in this case, right? So we don't do anything with either of these. Now, in the context of this problem, that means that two dominoes were standing straight up and they were just kind of counteracting each other. Well, not straight up, but they were just leaning against each other, right? Okay, but now you can see that we have no more dominoes that are leaning over. I really hope I did this correctly, so correct me if I'm wrong, but I think this is kind of what our state would be, LL, a bunch of characters, and I think that does match pretty much exactly with what they had in the output, so I think we're good to go. By the way, this the time complexity of this solution is going to be big O of n, because in the worst case, every single domino could be added to the queue and then popped from the queue. So basically big O of n time complexity, and also big O of n memory complexity, because our queue is going to potentially contain every single domino that was given to us in the input. Believe it or not, this is actually the simplest solution in my opinion. It's the most intuitive. There's actually a few more complicated solutions, but they're also just as efficient as this one, so I think this one is the preferred solution in my opinion. So now let's code it up. Okay, so now let's code it up. First thing you're going to notice is the dominoes are actually given to us in a string. It would probably be helpful for us to convert that into a list. The main reasoning is because as we're going to be updating the dominoes, you can't really update a character in a string in Python. So if we convert it to a list, we can update the character at any index of that list. Also, don't forget we're going to be using a queue. So let's do that in Python. A double-ended queue you can do like that. And then the way we want to initialize our queue is basically, first of all, I'm going to enumerate through all the dominoes. So our list of dominoes, we're going to get the index and the domino. That's what we're doing in Python here. I is the index, D is the domino. We want to add all the dominoes that are not standing straight up to our queue initially, right? Just like we did in the drawing, we want to queue.append each domino if it's not standing straight up. And actually, we're going to be adding a pair of values to our queue. So we're going to actually include the index, because you're going to see that the index is actually going to come in handy because, you know, after we pop a domino from our queue, we want to know the index of it so that we can check the neighbors of that domino. Okay, now the code is going to be pretty much similar to any queue problems where you continue the loop until your queue is completely empty, and each iteration of the loop, we just pop the element from the queue. In this case, we're going to pop the leftmost, but from that, we're going to get an index and a domino. So there's two cases, remember. The domino could be a left domino or it could be a right domino. We know it's not going to be standing straight up, because if it was, then we wouldn't have even added it to our queue. So if it's left or right, we know that the simple case, the more simple case, is the left one, because in that case, all we really have to do is check that its left neighbor is standing straight up, because that means we just tipped our left neighbor over. How do we know that our left neighbor exists and is standing straight up? Well, first of all, I has to be greater than 0, because if it's 0, that means we don't have any left neighbors. So if I is greater than 0, and if the left neighbor, which we can get from dom, index I minus 1, you can see that the index is helpful here. If I minus 1 is equal to a dot, that means our left neighbor is standing straight up. What does that mean? Well, we're going to, first of all, add our left neighbor to the queue. Its index is I minus 1, and its value is now going to be left because we just tipped it over. And don't forget to actually update it in the dominoes list itself, because remember, that's what we're actually going to return in the end. I minus 1 is now going to be left. And that's pretty much all there is for the left case. The right case is a bit more complicated, because as we're going to the right, there could be more dominoes to the right that we haven't seen yet. One thing you might notice though from this code is we have two nested if statements. We could actually get rid of the second one and combine it with the first one, but I think it's a little bit less intuitive if I just wrote that straight off the bat. So let's do that. And now the opposite case. First, we want to check that we do have a right neighbor. How do we know if we have a right neighbor? Well, I has to be less than the length of dominoes minus 1. There has to be at least one domino to the right of it, and that domino has to be standing straight up. So I plus 1, actually, to make this a bit more clear, let's just say that I plus 1 is less than the length of domino, right? So that basically says that I plus 1 is a valid index. So then we use that index and then check if it's standing straight up. That means we could potentially knock it over, but we can't knock it over if there exists an I plus 2 index. Basically, that means there's actually another domino to the right of this one that's standing straight up, and that domino happens to be a domino that's leaning to the left. So if that's the case, which we can check pretty easily like this, that means we can't knock this domino over. That means this domino is stuck. But what should we do now? Well, we should pop from the queue one more time. The reason we're doing this is if we don't pop this domino right here that's leaning to the left, that means on the next iteration of the loop, we're going to visit that domino again, and then our code is going to run, and then this first if statement is going to run. And what's going to happen is this left domino is going to knock over this one, even though it shouldn't, because this one is in between two dominoes, a right domino and a left domino. So this one should not be knocked over. That's why we're popping this left domino to make sure that that doesn't happen. So we're basically skipping this domino, but that's only if that left domino exists to the right of this one. If that's not the case though, then it's the slightly more simple case where we just do the generic thing, basically tip this domino over and then append it to the queue, just like we kind of did up above. So I'm actually just going to copy and paste these two lines, copy paste, and then say, okay, domino, in this case, not I minus 1, but I plus 1 is going to be set to a right domino because it just got knocked over. And also we append it to the queue, I plus 1, and it's a right domino, not a left domino. Okay, and believe it or not, that's the entire code. I know it kind of...
No, it just cut off, dude. What an interesting solution. Wow. Oh, the color faded from it. Okay. 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 Collections. Import DQ. Right, we loop through. Okay. We create our queue. Q is equal to DQ. We want to make it a list too. Hate spelling dominoes for some reason. So dom is equal to a list of dominoes. In enumerate. Q.append. Oh! For ID and enumerate dom. We would if L or D is equal to R, Q.append
the index, because you're going to see that the because
looking for dots. Oh, we're doing the same thing. Append ID. I'm gonna like this comment. Seems like I'm not the only one that thought stack. So, like the penguin. Go to software engineer. Stack by pop, right? So then we would check, okay, well, if the index, if equal to L equal to L, then what do we do? Stack.append. If domino is equal to R and And I plus 1 is less than or equal to the length of so is equal to R, and I plus 1 is less than the length of I think this would be equal. I plus 1 is less than or equal. And domino x plus 1 is equal to a dot. If domino index plus 2 is equal to an L, right? Then we can pop stack q dot pop left. Otherwise, we would do the same here. Otherwise, we would just return our dom. Return a string. Return. Stack, dude. What the hell? Stack Q. I got another stack here. Setting index is out of range. Q dot append. Index minus 1 L. I plus 1 L. Should be I minus 1. String index is out of range. Why are we getting string index out of range? Oh shit. Okay. Whoops, this is meant to be index, that's why. Call it index here. Whoops, sorry guys.
To the right, can't knock it over. More popping and paste these two lines.
DOM index. You go to L. String index is out of range. Okay, so we got domino R is equal to domino is equal to R. And I'm getting confused here with all the different things. Dom, domino, D, like, should have kept it all the same anyway. It's my fault. And dom index plus 1 is equal to this. Okay, then we check. Okay, well, if dom index plus 2 is equal to L, we pop left, right? If index plus 2 is less than the length of num, less than or equal to the length of nums minus 1, and dom index plus 2 is equal to L, we pop. Else we append we get R. Index out of range. Why are we getting it out of range? Because we're comparing to this one, and we should be comparing to this one. So we know that it's in range here, right? maybe is it this? Is less than like dom. And dom index plus 1 is equal to this. If index plus 2 is less than or equal to, is less than, I'm going the length of nums, that's why. Length of dom. And dom index plus 2 is equal to L. We pop, we append to the Q.
A left domino. Okay, and believe it or not, that's the entire code. I know it kind of... Not a left domino. Okay, and believe it or not, that's the entire code. I know it...
Q dot append. X plus 1. Bro, what is wrong here? Dude, I'm so lost. Like... Right. We're not checking this test case over here. I don't know why it's not working. Bro, what? I'm literally so confused. I don't know why this is not working. Literally have no idea. Do I really have to copy this guy's code, bro? Oh my god, I'm just gonna do it. While Q. ID. Go to Q.pop. Oh my god, dude. Is it this, bro? Shit, where was it? Should be pop left here. Is that literally our issue, bro? Oh my god. Oh my god. Jesus, man. Take a look at this guy's stack solution. Or even digits, dude. What? Bro, what is this, bro? Like, jeez, man, like, bro, what an 100 lines code for a solution, bro. What the? What is this in, bro? Swift. Huh. Man, that problem took like literally an hour, dude. Like, um, take a look at word break. TP problem, man. Oh, so disgusting, bro. Oh my god. Turn a string S in a dictionary of strings word dick. Return true if S can be segmented into a space-separated sequence of one or more dictionary words. Bro, I don't even know what this means, bro. What is string S in a dictionary of strings? Dictionary of strings and word dick. Return true if S can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Return true because Leetcode can be segmented as Leetcode. Apple pen. Oh, because we got apple, pen, apple. Cats and dog. Cats, dog. It's false. Okay, I think I understand. Definitely interesting. Okay, we want to think brute force first, right? How can we brute force solve this? The easiest way to solve this problem. Okay. Okay, it's a list. So I guess we could maybe like keep generating the string maybe. Like maybe we generate this. Alright, this is in there. Then we start from here and generate this. Would that work? Apple. Could that work? I don't know. Seems like kind of a stupid solution, but hey, we're looking for a brute force solution here, right? Like, all strings of word dick are unique. S and word dick I consist of only lowercase English characters. I don't think that would work. That the same word dictionary may be used multiple times in the segmentation. Okay. Bro, this is so confusing. I'm gonna start spitting some ideas. I am working on 139 word array. Okay, so my brute force was kind of correct. So my idea here, my intuition here, what I'm talking to GPT about is I'm saying, okay, I'm working on 139 word rate. I'm first trying to obviously do a brute force solution. My intuition is to create all the different, I said permutations, but I guess like permutation is probably the wrong word here, but I always forget, man. Permutations, arrangement of objects in a different order. I think permutation are ordered. Maybe it is the right word. I don't know, but okay. Point is that all the different combinations that are valid, right? And then we transfer this into a set so we can use that for O of 1 lookups, right? Because looking up in a set is O of 1 constant time. So instead of generating permutations, which mean rearranging characters, not what we want. You want to explore all possible ways to break S into substrings and check if the segment is in the dictionary. For each I from 1. There's 2 or more. That recursion. We're gonna need some sort of like, oh shit, man. Gonna need some sort of eye here. Okay, maybe a cur as well. Recursion, 0 cur. Cur would be here. Okay, we want to keep going until our eye. If I is greater than, sorry, if it's a base, right? Okay, if I is greater than S, like the best hardest one. And what do we want to do? Well, I guess we can like return false, no? Something like this, right? We can check, okay, well. Maybe we don't even need a cur because we'd be generating these strings, right? So. Addict. Convert it to a set, right? Let's do substring is equal to S from up to I'm not sure, man. Starting index of the substring you're valuing, not how far to go. Oh, sorry, I meant the other way. Whoops. I didn't mean this. Up to I. You don't need cur unless you're trying to build the actual path for true and false result. It's unnecessary. That's what I thought. That's why we got rid of it. Reach the end of the string, meaning everything before it was successfully segmented. If I is equal to 0, I want to return true. For j in range I plus 1 I plus 1 to the length of s. Okay, we want to check the substring is equal to I to j, right? Want to call check substring helper function, right? Take substring, we pass in substring, okay? If substring is equal to true, then we want to do something, right? We want to probably recall this like recursion and instead pass in. I always forget in Python, slicing Python. Start and begin the slice inclusive. The end is exclusive. So and we'd actually have to pass in j, right? We pass in j. Recursion j. Okay. Like def check substring I. Sorry, so substring, right? If substring in set word return true, else return false. Okay. Check substring, we pass in the recursion. See what this thinks. Call the function but don't use the result. Okay, substring s ij. If check substring, okay, then if recursion j, we would return true, right? Otherwise, we would just return false. Okay. Guess we would just return the this here. 2 were given. Oh. Why the... It's telling me we need a +1 here, but I'm not sure. I'm not sure why. not including j. So to include the entire remaining string, you need to allow j to go one past the index. Okay, this should give us a TLE now. Okay, time limit exceeded. Okay, so we got the brute force solution going. Now, how can we add DP to this, dude? That's the hard part. Okay, maybe we can like somehow store the substring, maybe? If we've looked up that substring before. Because we are generating substrings here, so maybe we can like have some sort of like DP like hash map here. J in range A with substring. Okay. It's the recursion really that like this is all one, the checking here, right? My intuition is to use a hash map to store what is it? Shit. Previously computed substrings. Is this correct? Let's go. My intuition is exactly right. Let's go. You're using a hash map dictionary to memorize previously computed substrings and indices, so that function doesn't repeat the same expensive work. Why? Is that a most efficient approach? It's position based, meaning can I break the string starting from index size? By substring SI. This works too. It's a bit more costly, but because hash map is still already computed values, and for this problem, it's best to use true false. Why are we... Okay, apparently we can just use I. I thought we would use IJ like this and store this as a key, considering this is like the word, but apparently you can just start from I. So I guess, well, if I in DP, then we would just return DPI, right? Okay, otherwise, if recursion J and DP J is equal to true. On DP, word break. Let's go. I'm good with all these, I think. They don't have Q in here, I just realized that. Good with trees. Good with heaps, I think. I have good intuition with heaps. I've okay intuition with grass. Backtracking, okay. 1DP, kind of tough. I don't know, like... Just gotta keep going, man. Anyway, I might be back a little later. We're gonna go play some pickleball, get some exercise in. Yeah, I might be back a little later. Maybe I might do another problem later. But ooh. But yeah, see you guys a little later. Appreciate it.